Welcome back, ladies and gentlemen. I trust you had a very nice spring break. Got a little bit of time away. I know traveling and going places was really not in the cards this time around, but nevertheless, I hope that you had a nice time with your family, enjoyed being away from school. Now we're going to pick up and complete where we left off right before spring break on chapter 13. So we had on Friday, just over a week ago, 13.4 Part A, we talked about a process called sublimation. I just wanted to quickly run through this. So sublimation is the process of a solid going directly from its solid state to its gaseous form. It skips right over being a liquid, goes from solid to vapor. And that process is called sublimation. And there are several substances that will undergo sublimation. And we looked and talked about two of them, iodine and carbon dioxide, and we mentioned those again today. So that same process, but going in reverse from vapor back to solid, deposition. So hopefully if you have your notes in front of you, you have those two terms. They're really important terms. I mentioned previously iodine. Iodine goes directly from its solid state to its gaseous form. Because it has a very high vapor pressure, the vapor pressure is greater than the atmospheric pressure, so therefore it can escape directly from solid to gas. One that is very common actually is solid carbon dioxide, also known as dry ice. You can buy that in some supermarkets. Many a time you've probably seen them in restaurants. You see the fog that it releases as it goes from solid state to gaseous, and it sets up an ambiance, and they have them in a lot of decorations in many restaurants, including at Disney World. If you go to any of those Dinosaur Land or those type of places, they have a lot of that. It creates a nice illusion, a nice effect. But the process is sublimation, going from solid into the gaseous state. Now that's used a lot in shipping, as we talked about in the last lesson, because it doesn't become a liquid and cause the cardboard to rip. So it is used a lot in shipping in all kinds of industries. We looked at this checkpoint question last time, but I want to do as a quick review just to look at it with you again. Which of the following describes a solid undergoing sublimation? So take a moment, look at A, B, C, and D. Think about which one you think would be correct. Hopefully you chose A. A would be the correct response. So when we talk about sublimation, the vapor pressure must exceed the atmospheric pressure in order for the substance to go directly from solid to gas. This new lesson, which is 13.4 Part B, is phase diagrams. So you may think, what is a phase diagram? Well, we know the three phases, solid, liquid, and gas. So a diagram is going to show you all three of those phases. And it is a graph. It's a graph, and we're familiar with graphs already, but we're going to relook at and talk a little bit about a phase diagram. So when you talk about the relationship among solid, liquid, and the vapor state of any substance, it can be represented on a graph, and that graph is called a phase diagram. So there's another vocabulary word for you. So the graph, so we're familiar with graph. On a graph, we have the y-axis, we have the x-axis. And on a phase diagram, the x-axis is the temp. It's the temperature, and that's in degrees Celsius. When you look at the y-axis is pressure. And the pressure is typically going to be in kilopascals or in atmospheres. Those are the two most common ones that we will use on a phase diagram. So the phase diagram gives the conditions of temperature and pressure at which a substance exists as solid, liquid, or gas. All substances have a phase diagram, and they can be represented and looked at to determine at what temperature or pressure each one of those three phases exist for whatever substance you're looking at. So this here is really important. When you look at what a line represents, so please get that in your notes, a line on a phase diagram. What does it represent? So the condition of pressure and temperature at which two phases exist in equilibrium are indicated by a line on the phase diagram. It's typically a curved line, but nevertheless, that line represents equilibrium between the two states, whether it's a solid and the liquid or the liquid and the gaseous state. That line says it's in equilibrium. So the temperature and the pressure along that line indicate equilibrium. Real important concept, and that is the beauty of a phase diagram. So let's look at a phase diagram. So here is one for water. So we're very familiar with a lot of things about water, so I want to look at this with you here real quick. So first off, we notice the curved lines. We see some color coordination. So first off, we're looking here. We see solid here in this purplish color. We see liquid here in the yellow, and then we see vapor in this velvetish color. Right away, we see some dotted lines. Right away, hopefully you pinpointed 100 degrees Celsius, and you look up here and 101.3 kilopascals, and right there is our normal boiling point, When you look down on the other side, you see here at 101.3 and at 0 degrees Celsius, we know that that is our melting and freezing point. We learned already in this chapter that the freezing point and the melting point were the same if they're in equilibrium, and this is what it's showing you. So let's look at this far side here on the right. What if we raise the pressure? So we raise the pressure up above 101.3. Look at what happens as we go up. Say we come up to about right here. Following it across and marking it right there and looking down, look at what happened to the boiling point. The boiling point just went up. So the boiling point is directly related to the pressure, and that's how a pressure cooker works. You probably have them at home. You may have seen them in use. What happens is the pressure builds up above the liquid that's in the container, forcing down on the substance that you have in that container, thus making the boiling point raise because it can't escape. It cannot escape into the gaseous state because the atmospheric pressure above it is much higher than the normal atmospheric pressure. So that's why the boiling point is much higher. A lot of times 110 degrees Celsius or something of that nature, typically 100. Here you might say, well, here it is 110 degrees Celsius. So by raising the pressure, we raised the boiling point. Now on the same side here, let's look at what happens if we lowered. So we come down here and we mark off about right here. We follow across here. Look at what happened to, we come right up here. We're going to probably be somewhere about 90 degrees Celsius here. So that's the concept we talked about in this chapter. When you go up into a high mountain, if you go up into a high mountain, the pressure around you drops. The atmospheric pressure drops as you go up in elevation. So now with that pressure drop, the boiling point drops. So the equilibrium between liquid and gaseous form is now at 90 degrees Celsius. And that becomes the boiling point at a higher altitude, which means a lower pressure. Now when we look at the other side, we notice that we have another line, this line right here, and that's separating the solid from the liquid state. So as you go up in pressure, look at what happens to the freezing point. If you go up in pressure, the freezing point drops below 0. As you drop in pressure, look at what happens. Now you're coming down, following it across here. If you're dropping in pressure, now your freezing point actually elevates a little bit. So When we look at that, we're going to be talking about that in chapter 15, and that's called colligative properties of water and substances. So we'll look at that a little bit later. All right, so here you see the red line marking the equilibrium between liquid and vapor. Here you see the line indicating and the arrows between liquid and solid and between solid and vapor, as this arrow right here is representing. So that's how you skip liquid. By this pressure and temperature change can go directly from solid to vapor rather than going into the liquid state. So there's this line and it's circled right here for us. It's called the triple point. A phase diagram shows the relationship, and where all the three lines meet, that's called the triple point. That is the point at which any substance is at equilibrium between solid, liquid, and gas. I know it's kind of odd to think that, but a triple point is pretty neat. A substance is in equilibrium with all three phases. So let's define that. A triple point. A triple point describes the only set of conditions at which all three phases exist in equilibrium with one another. That is an important definition, so please get that into your notes. The triple point describes the only set of conditions at which all three phases exist in equilibrium with one another. So let me back up 1 second here. So when we look at this right here, the triple point for water, we notice it is a low temperature just above the freezing point, which is 0 degrees Celsius. So it's 0.016 degrees Celsius. When we come over here, it is almost a vacuum at 0.61 kilopascals. If we would be in the classroom today, one of the neat demos I was going to do was I have a machine that creates a vacuum, and I was going to put water in there that was just above freezing, and I was going to pull the air out, creating almost a vacuum, and show you the triple point of water. It's really cool to watch. You see the water bubbling because it's boiling. You see solid formations of crystal in there, which is freezing. And you see in the container precipitation running down. So it's evaporating and condensing down the side. It's really cool to see. But we do have a picture. I don't have that demo to show you, but I have a picture here in a boiling flask right here. So notice on this picture, see the little bubbles forming right there. That means this is at its boiling point. You can very clearly see ice on the sides there, this crystal structure of ice. What you don't see in this diagram is it is evaporating, condensing, and then running down the sides in its liquid state. So once again, it tells you it's not important for you to know these two, the temperature and the pressure, but just understanding the concept of it. And all substances have this triple point, and you can find them on any phase diagram. So we began this section talking about a case file, talking about how water moves in Earth's atmosphere. It's called the water cycle. You're going to learn a lot more about that next year in biology. But for now, we introduced it because it's a big concept, condensation, evaporation in chemistry. It has everything to do with the kinetic energy. We talked about kinetic energy being the energy of motion. So as the water molecules overcome the force of attraction because of their kinetic energy, they can escape into the atmosphere. So they overcome the attraction to itself, overcome the atmospheric pressure that's around it, and it escapes. That is why when you go out after a rainstorm, you see puddles. If you go out, I don't know, 15, 20 minutes later, depending on the temperature of that day, you may notice that the water is gone. So it evaporated because at some point, all of the molecules of water will overcome the attraction and the atmospheric pressure and escape into the atmosphere. So it's going to go up into the sky. It's going to condense because it cools. As it goes higher, it cools. As it cools, the kinetic energy falls. So now attraction forms again, and now it condenses. And that's what you see in the upper atmosphere when you look up in the sky and you see clouds. It's condensed water vapor. Once it condenses, it will precipitate, and that's the rain that we see. It'll rain. And that is the water cycle. And that's what talks a little bit about that here, describing that. Here's our last checkpoint of this particular chapter. Describe the meaning of a line in a phase diagram. Take a second and think about that. Well, hopefully you remember that a line, curved line coming up, and then you have another line typically running down like that. And here you have your solid, you have your liquid, and you have your gaseous states. That line means equilibrium. And that's what it says here. Along a line in a phase diagram, two phases are in equilibrium with each other. Well, ladies and gentlemen, that is it for this particular lesson today. 13.4 Part B is complete. So we talked about sublimation. We talked about a phase diagram. We have some terms that you should have got into your notes in this particular lesson, which was phase diagram and triple point. So that is it for this chapter, ladies and gentlemen. I'll have another virtual lesson coming up here on Wednesday, and we will review all the key concepts of chapter 13. Thank you for watching. Go in peace.